Poster, clock synchronization for distributed wireless protocols at the physical layer, was written by Omid Abari, Harihan Rahul, and Dina Kahabi, of who are all students at MIT at the time. And it is a paper that seeks to solve the problem of out-of-sync clocks in the physical layer of wireless networks. The physical layer is the first and lowest layer of the Open System Interconnection Model, or OSI, OC. OC is a way of breaking down the computer into different levels of abstraction depending on what layer of OC you're talking about, with application being what most users see, and the physical layer being a way to synchronize communication on the bit level between devices connected between cables or wireless networks. Traditionally, each node at the physical layer performs its signal processing independently. This means each node uses its own clock, which is created from a signal produced by a crystal oscillator. Typically, a signal is around 10 MHz, but since each node is using its own crystal, which is slightly different from the one next to it, it creates slightly different sine waves, which brings into the problem of superposition and can cause errors in the system. This is not a problem for wired networks, as a single oscillator can be used by connecting all the nodes to this one oscillator. But in wireless situations, that would completely defeat the purpose and the benefits of it being a wireless network. It is also unacceptable to transmit the low-frequency sine wave through antennas because it is against FCC regulations to transmit such low frequencies. And more toward the point, the antennas that capture these low frequencies are too large to be practical. AirClock was devised as a solution. AirClock works by scaling two sine waves to be transmitted in white spaces of the electromagnetic spectrum. The wanted frequency is stored in the difference between the two sine waves, so a 10 MHz wave would result in a 175 MHz and a 185 MHz wave being transmitted. After the two waves are sent, the receiver takes the signals and multiplies them by themselves and then applies a bandpass filter over the difference between the two signals, creating the 10 MHz wave. This system simplifies other more complex solutions, only needing an amplifier, mixer, and filter, as opposed to needing an extra 3 steps in other traditional solutions. The AirClock system was tested along with traditional independent clocks and signal clock wired systems. This was done by transmitting OFDM packets using 64 QAM modulation. The received signal is then estimated after modulation, as seen in the graphs. AirClock and signal oscillator systems were found to produce very similar results, while the independent clocks are not in sync and thus cause a rotation effect on the data points. In summary, AirClock solves the superposition problem of wireless networks on the physical layer by transmitting two higher frequency signals and taking the difference.